Bismillahirrahmanirrahim. Welcome to another video under ELE424 Analog Electronics 1. We have completed the DC biasing circuit. We are now starting the AC small signal analysis. This is the video pack 3, video 6, starting with the AC small signal model. You should be having the slides from the learning platform, ELE424DL. AC small signal model, BJT set 6 PDF file. I am Wan Fazli Dahanim Abdullah. I am from Faculty of Electrical Engineering, UiTM Shah Alam. So the topics covered in this BJT AC small signal analysis is, as usual, we'll start off with introduction, and our introduction will be quite lengthy so that you have a sense of appreciation of what is covered in the theory and the calculations that are involved in this topic. And then we will first look at the AC equivalent network and BJT transistor modeling so that we know how to prepare our amplifier for the AC analysis, and we will also have a look at the RE transistor model before we actually go on to the fixed bias, emitter stabilized bias, voltage divider bias, emitter follower common base, and collector feedback amplifier. All these circuits have been covered in the DC biasing circuits in the previous 5 video subtopics, but for this video we will just look at these 3 main topics first in preparing ourselves to do the AC analysis, and we'll finish off with the effect of RL and RS when I think this should be about another 2 or 3 videos down the road. So introduction, we will first have a look at the concept of amplification in the AC domain, and then we will look at our journey from DC to AC analysis. The journey from the first 5 videos to the next 3 or 4 videos, the first 5 videos being the DC biasing circuit, and the next few videos down the road here will be on AC analysis. So for the introduction, let's see what we know so far. We've done many videos. Okay, I think this is the 13th video, and what we need to know next for BJT amplifiers in general. So we know that BJTs can be used as amplifying devices that enable voltage, current, or power level of an input signal to be increased, i.e. amplified. Okay, so in order for a BJT circuit to amplify without distortion, if we're talking about linear amplification, the BJT needs to be DC biased in the operating region that is required. DC biased is what we have covered before, and if we can recall, for linear amplification, BJT should be in the active region with the emitter based forward biased and collector based to be reverse biased. The BJT in the amplifier here is biased at a Q point by a DC biasing circuit, as we already know how to do, and now it is fed with an AC signal that it needs to amplify. So we know how to analyze the DC requirements from the previous subtopic. We know how to set the input parameters and to get the Q point that we want. And now the question is, how do we analyze the circuit effect onto this AC signal with the BJT already biased at the Q point? So firstly, it depends on the amplitude of the AC signal. In general, amplitude of the AC signal with respect to the DC operating conditions. So if the magnitude is small and will not change the operating point significantly, we'll look at this in the next slides, we can use small signal analysis method. Otherwise, the treatment will follow large signal analysis. So just to further emphasize on the point, in small signal amplifiers, the main factors are usually amplification, linearity, and magnitude of gain. So a voltage amplifier provides voltage amplification primarily to increase the voltage of the input signal. Okay, there is also another category which is power amplifiers, and power amplifiers require large signal analysis, of which is not covered in this chapter. So I'm just pointing it out so that you know that there is you'll be seeing this other kind of amplifiers later on. Okay, for this chapter we will only look at small signal amplifiers. So amplification in the AC domain, In this slide, we'll talk about the conservation of energy a little bit. So amplifiers are intended to produce output sinusoidal signals that are greater than the input sinusoidal signals, i.e. the output AC power is greater than the input AC power. The question is, because of the conservation of energy, where does this power come from? The DC power actually provides the necessary output AC power increase. So the DC biasing circuit not only biases the BJT to be in the Q point, but it also provides the DC power that is necessary for the amplification to take place. To illustrate, now let's consider a circuit that has a DC supply here connected to a resistor, where we know that the current will be a constant value of current. Then let's consider a device added to it, just like a BJT with a controlling signal, just like a small signal AC. So this is what we're considering here. The control mechanism is such that the application of a relatively small signal, this is a small signal, and this small signal comes in as a control mechanism. Once it enters the circuit, it can result in a substantial oscillation of the output circuit, like here. Okay, so what happens here is that the output current has an AC component riding on the DC value. Okay, and it is amplified from the small value here, keeping the conservation of energy in place. So this slide is just to illustrate that point. Another illustration is to show the effect on BJT output behavior, output characteristics with AC input. So let's consider this common emitter configuration amplifier circuit where we have a BJT here, and all the DC biasing circuits have been done with all the values of current, IB, IC, IE have all been calculated. So the purpose of this slide is not to do a calculation example, it's just to illustrate how an AC signal affects the output characteristics of the BJT. So the CE amp with the DC biasing conditions have been calculated as above. We want to see the effect. We know that IB is 46 microamps here. We want to see the effect when the AC input signal is fed to the base at a 60 microamp peak to peak. So here we have a 46 microamp. This is just for illustration purposes. It's just all these values are not specific for anything. It's just for this example. So we know that IBs is 46 microamp, and with this voltage divider bias common emitter configuration from our previous DC biasing circuit, we know that we can draw a load line, and with this load line we can have the intercept, the x-intercept at VCE is equals to VCC, and we can estimate the current saturation value that is to be avoided. So in this case it has been found to be 9.2 milliamps, and the Q point here is at the point shown here with IB equals to 46 microamps and ICQ to be at 4.8 milliamps and VCEQ to be at 5.8 volts. Alright, okay, fine. So now what happens when V in oscillates with a 60 microamp peak to peak? So the V in goes into IB, which means IB will now change along this load line, okay, going 60 microamps peak to peak. So this is how IB changes, and we are drawing the how it changed the sinusoidal effect next to it. Okay, just to illustrate this. So it's going from the Q point, which is 46 microamp, about 50 microamp, let's just estimate, going up 30 microamp to 80 microamps, and then it goes down another 30 microamps, making it 60 microamp peak to peak, down to 20 microamps. So 50 plus 30 to 80, 50 minus 30 to 20. Alright, so this is what happens to IB. So, and when that happens to IB, what happens to IC is such that when it is at 80 microamps, IC is now 7.7 milliamps. And when it goes down back to 46 microamp, IC is 4.8 milliamp at the Q point. And then when it goes down to the negative peak of 20 microamps, okay, the IC value also goes down to 2 milliamps, and we can see that VCE also oscillates from the Q point at 5.8 volts down to 2 volts and up to 9.34 volts. Okay, this is how it looks like on the output characteristics. Just this point of operation going along the lines of the load line. You can have more information on this at the electronics tutorial website. You may want to listen to it in a different kind of delivery, so you can have a look at that website. It's worthwhile you to check that out. Now, before we leave this slide, I'd like to also point out that if we incorrectly design our amplifier circuit and set the biasing Q point at the wrong position on the load line, or we apply too large an input signal to the amplifier, the resultant output signal may not be an exact reproduction of the original input signal waveform. In other words, the amplifier, if it leaves the active region, it will suffer from what is commonly called amplifier distortion. So the next slide is an example of amplitude distortion. Okay, so again with this amplifier system, when there is an amplitude distortion, when the input amplitude becomes too large, clipping becomes substantial and forces the output waveform signal to exceed the power supply voltage rails here, causing parts of the waveform signal becoming flattened or clipped off. To avoid this clipping, the maximum value of the input signal must be limited to a level that will prevent this clipping effect. There can also be other types of amplitude distortion, as well as frequency distortion and phase delay distortion. Okay, so these are just to show, like, let's say for example here, but these are due to harmonics here. Okay, it's supposed to be the blue line, but because of the distortion, it becomes slightly different. So anyway, if you want to read further on distortion, again, the electronics tutorial webpage does good treatment on it. Okay, so now moving from amplifier from DC to AC analysis. Okay, for the analysis on the effect of the amplifier to the input signal, we will treat DC and AC separately using superposition theorem. Okay, so you may as you do this later on, you may even forget that you're using superposition theorem, but I would like to explain that even though the signal that goes through BJT is DC and AC at the same time, we still we will be treating it separately, but it can be added because of the superposition theorem. So the superposition theorem allows the DC and AC analysis to be added, a complete DC analysis of a system to be done before considering the AC response, and then once the DC analysis is complete, the AC response can be determined using AC analysis. And moving from DC to AC analysis, to do DC analysis, we already know this, I'm just repeating myself here. We draw the DC equivalent circuit and do the analysis of the input loop and the output loop. Okay, there will be parameters from DC analysis that you would have found from the previous topics, and these parameters may be required in the AC analysis. Then once we're done with the DC analysis, we go on to the AC analysis, where we draw the AC equivalent circuit, the BJT is replaced with an AC model, and the amplifier circuit is redrawn and is labeled as a two-port network. Then we do circuit analysis for input and output impedance of Z in, Z out, and gain, for example AV. The complete response is addition to the DC of the DC and AC analysis, which you add together. Okay, so AC equivalent network, BJT transistor modeling, where we will look at two-port network and finding the AC equivalent network. So AC analysis. When the BJT amplifier DC analysis has established that the BJT is operating at the Q point that is required, we enter AC analysis. the BJT is replaced with the AC model when doing an AC analysis, and for this course, the RE model is used. For RE model in a common emitter configuration, the value of IE is required from DC analysis to proceed with AC analysis. So when I said earlier in the earlier slide that you will be needing a parameter from the DC analysis for the AC analysis to begin, for this common emitter configuration, that value, that parameter that we need is IE. So we can calculate all the values that we need from DC analysis. This value of IE is required for AC analysis, and we will see why later. So the previous slide, just the previous slide before this, the content slide, says that AC analysis involves from parameters from DC analysis, which here I have explained is going to be IE. You need to draw an AC equivalent circuit. You need to replace the BJT with the AC model, and you need to treat the whole amplifier as a two-port network for you to analyze that in, Z out, and AV. Okay, so this section of AC equivalent network explains the AC equivalent circuit, how to draw it, and the treatment of the amplifier circuit as a two-port network. And before we can proceed, as usual, the slide turns yellow, and this is a revision on capacitance and coupling capacitors before we proceed. We've studied capacitance many years ago, so in school, but let's just have a quick recap on it. So capacitance are reactive devices, which means that its impedance depends on the frequency. So to low frequency signals, C has high impedance, and to high frequency, C has low impedance. Okay, so in general, the role of coupling capacitors, sometimes you have capacitors added at the end. So the role of coupling capacitors is to allow only the AC signal to be passed from one circuit element to another. So if you have a coupling capacitor in the middle, the capacitor blocks the DC signal from entering the second element and only allows the AC signal to pass through. You can have a look at this more under the learning about electronics, just to reinforce what you already know. So capacitors in the amplifier. So consider this CE amplifier, the common emitter amplifier, as an example to aid our discussion. So we have C1 and C2 here. So BJT amplifiers have coupling capacitors C1 and C2 at the input and output to ensure that only the AC component of the input signal is taken in or sent out. This means that the common emitter amplifier is biased only by the DC biasing circuit. Okay, so any other DC levels from the connecting circuit that comes from here is blocked by C1, thus it does not interfere with the biasing levels that set the Q point. Because when we design for the Q point, we only design values of, in this example, R1, R2, RC, and RE. But what comes before this is not, so it should be blocked. So C3, okay, we have C1 and C2 as a coupling capacitor, but C3 here is a bypass capacitor. There is a reason for the bypass capacitor, and I'm just saying this out here, although it's not covered quite in this chapter. So it is sometimes added to increase voltage gain and to avoid fluctuations in IE that affects RE, because later you will find RE being linked to IE. RE is 26 millivolts divided by IE. So the DC levels from the biasing circuit goes through RE to provide the feedback and stabilization, but the AC is channeled to the ground by the bypass capacitor. So when doing DC analysis to form DC equivalent circuits, because of the fact that capacitors are reactive devices, the capacitors are treated as open circuits. But for our AC analysis, to form AC equivalent circuits, okay, because now it becomes very low impedance with the AC, capacitors are treated as short circuits. So forming the AC equivalent circuit, to form the AC equivalent circuit of a given amplifier, as in our example, here was the voltage divider bias common emitter configuration, which we will use as an example, but it applies to all other treatment of amplifiers. Set all DC sources to 0 and replace them by a short circuit equivalent. Okay, set all DC sources to 0, becomes ground. Okay, and replace them by a short circuit equivalent. replace all capacitors by short circuit equivalent. So this was C1, C2 and C3. And remove all elements bypassed by the short circuit equivalents introduced by steps 1 and 2. This is step 1 and step 2. So this bypass capacitor provides a short circuit, so RE will not be present because there is a bypass capacitance which shorts it out. Now we need to redraw this network in a more convenient and logical form and label the current voltage parameters of a two-port network. So the slide will go back to a revision slide on the two-port network before we proceed. Okay, you may or may not have covered two-port network in your studies before this. Even if you haven't, as a topic, it's not difficult. What I explain in this slide is enough for you to proceed. Any network with input and output terminals, such as the transistor network here that we had previously, can be represented by a two-port network with the voltage and current notation shown here. Okay, so any kind of network can be represented by this block system. This is what you call the two-port network with the voltage and current notation shown. That's all that is saying. So even though the network appearance in the system block may change, it could be a voltage divider bias, it could be a emitter bias, stabilized bias circuit, it could be a collector feedback circuit. Okay, the quantities represented by the reduced network must be the same as defined by the original network, with these notations represented in the same direction. So you have I in for the input current and I out for the output current, and the notation is such that I in enters this point into the system. I out also enters the system at this point where V in and V out has its positive terminal. Z in is the input impedance when looking into the system across these two terminals. Okay, and Z out is the output impedance when looking back to the system. V in and V out has positive terminal at the point that I in and I out enters the system. Okay, you cannot change these notations because this is the notation that is agreed for all two-port networks that is represented by the system. And if you want to find voltage gain, it's going to be V out over V in, which is the voltage gain of the system, and current gain is I out over I in. Okay, back to the topic. Now the AC equivalent circuit as a two-port network. This is what we are going to do. We are going to redraw the circuit with the BJT replaced with a model, and we will treat the circuit, we will label it with two-port network parameters of I in, I out, Z in, Z out, and V out and V in. So we redraw the network in a more convenient and logical form. Replace the BJT, this BJT here, with the AC model and label the current voltage parameters of a two-port network, and that is what we are going to do. Here we have already indicated I in to be the current that enters the amplifier, Z in is going to be the impedance when you look into the amplifier, and V in to be positive at the terminal that I in enters. Same thing with V out, positive at the point where I out enters, and Z out is going to be the impedance when you look back into the amplifier. And this BJT will be replaced by an AC model. Redrawing. Okay, also I forgot to point out that just like the DC biasing circuit, R1 and R2 is now parallel because they are both connected to the ground. Okay, so this is the RE model replacing the BJT. We will look at later, we will have a look at what this RE model is all about, and this is the model. So now we are ready to look at the model. First we will look at the model in common emitter configuration, and then we'll have a look at the theory or description or explanation behind the elements in the model, why is there, and a quick look at the model in common base configuration. So RE model in general, again, introduction to BJT AC model. We will replace, I'm repeating myself again and again because I find that sometimes when you're doing analysis you lose track whether you're in DC world, or you're in the AC analysis world. So we will replace the BJT with an AC model when we do small signal AC analysis. An AC model is an equivalent circuit that represents the AC characteristics of the transistor. So there are three models commonly used in analog electronics undergraduate textbooks, which is the RE model, hybrid pi model, and the hybrid equivalent model. But for this course, we will cover RE model only, and for future advanced courses with high frequency switching, hybrid models will be considered, but not for this course. But whatever model that you are using, the concept is the same. When you draw the AC equivalent circuit, the transistor that you are given, that AC model, whatever model that you have here, it replaces the transistor that you have in the amplifier circuit. Okay, let's have a look at the RE model in common emitter configuration. So we know that we want to replace the BJT with the RE model, and this is how it looks like. It consists of a resistor beta RE, a dependent current source beta IB, and an output resistor R out. To find the value of RE, okay, just this RE here, we need IE from DC analysis. Beta is the same beta that that is given from the previous, just as in the DC biasing circuit, and we will see how to find R out. Now the applied voltage Vin here, in this case, for this circuit, is equal to VBE, with the input current being the base current, because it so happens Vin is the same as VBE because there is no resistor here. Okay, you will have to look at the different amplifier equivalent, AC equivalent circuit to see whether Vin is equal to a VBE or not. So for the common collector configuration, the model defined for the common emitter configuration is normally applied. Okay, explaining beta RE. So what I'm going to do is that for each of this existence of beta RE, beta IB, and R out, we're going to explain why it's there. So at the input, base emitter forward bias junction input characteristics is actually just like forward bias diode. Okay, here, ignore the other parts first. This part here is actually just like a forward bias diode, and we know that VBE is 0.7 because VBE is actually just a PN junction. Now, if we replace it with a diode, we know that diode AC resistance is RD equals to 26 millivolts over ID. This is a concept of diode that was covered earlier. Okay, but the diode is still not a passive element. Okay, why have we considered the diode AC resistance here? Because diode is still not a passive element, and it makes analysis still not using passive element, which means that you can't use Ohm's law and things like that. So it is replaced by its equivalent resistance RE. Okay, this is represented by the diode AC resistance RE, where RE is 26 millivolts, and the current that goes through RE is our DC emitter current IE. Okay, but when we put it into this circuit here, it's still REIE, and the value of IE comes from DC analysis. In the RE model, the resistance between base and emitter earlier that we showed was beta RE and not just RE, because that is representing the input impedance value Zn in this case. So Zn is V input over IB. Okay, so V input over IB, which is VBE over IB, and when we do the Ohm's law of VBE equals to IERE, we will find that Zn is equals to beta plus 1 RE. Okay, in this case, here we're talking about the model itself. We're not talking about the voltage divider bias example anymore. Okay, I'm just reminding myself that I am now talking about the RE model. So input impedance is beta plus 1 RE, and because beta is typically a large value, this plus 1 is can be estimated to be not giving significance to the change in value. So Zn is approximated to be equals to beta RE, and that is why in the RE model the resistance is shown as beta RE. So typical values of beta is usually about 50 to 200, with values of beta RE typically a few hundred ohms to 6 or 7 kilo ohms. So plus 1 is not that significant. Now we explain beta IB and the existence of R out. In the model, IC is represented by a dependent current source. IC is equal to beta IB, and we know this from our previous topics because it is linked by this common emitter amplification factor here, beta. But in reality, IC characteristics have a slope in the active region. Okay, and when there is a slope, this implies there is a resistance. Now this slope is represented by R out. The steeper the slope, the less horizontal it becomes, the steeper the slope, the less ideal the transistor. So a good transistor has high output impedance. If it's a good transistor, this will not be steep. Okay, if it's a good transistor, it has high input impedance, which means R out is large, and the value of typical transistors, value R out is typically in the range of 40 kilo ohms to 50 kilo ohms. So there is such a thing here called the early voltage VA here. If the slope of the curve of all these curves is from the same output characteristics is extended until they reach the horizontal axis, they will intersect at a voltage, and it's called the early voltage, okay, VA. So for us to find what R out is, okay, output resistance R out can be determined from several ways. One is from early voltage, and using the value for the collector current quiescent point, Q point. Okay, so you have here, if you want to know what R out is, it's going to be Y over X, delta Y over delta X, which is ICQ divided by VA plus VCEQ, which is, and the inverse of it, because the resistance is from Ohm's law is V over I. Or you can find from the slope of the curve itself without going all the way down to the early voltage. Okay, if early voltage is not available, R out can be found from the slope of the curve here, or R out can be determined from the data sheet's H parameters, hybrid parameters. Usually, if it's not given in the question, then the plot will be given, or the value of early voltage is given. Alright, now before we finish off the video, let's have a look at the PNP BJT for common base configuration. Okay, this is now a PNP BJT, and this is a common base configuration. So just like the common emitter configuration, a forward bias diode is used to represent the connection from base to emitter. But in this case, our input current is IE, and when we draw the resistance, okay, it's directly RE, and we know from our previous coverage on the topic is that IC is related to IE by alpha, and alpha is a value that is very close to 1. So here, okay, so the direction is opposite, okay, compared to our previous slides of NPN common emitter, because this is a PNP BJT and not NPN. And in this case, we still have R out, the same R out, because it's the same transistor. RE is still 26 millivolts over IE, which you need to get from the DC analysis. And Zin is the input impedance when you look into the amplifier and you see RE. And IE is the emitter current that we obtain from DC. And Z out is, when we look into it, is going to be almost the value of R out, which is estimated to be a very large value in this case. But different treatment will give you different values, so depending on the circuit architecture and the values of the components that is involved and the parameters of the BJT. So we are now ready to do AC analysis on all of the amplifier circuits that was covered in BJT DC biasing circuits. See you next video. Please do the tutorials and attend online discussion for more question and answer engagement. Thank you. Assalamualaikum.